This is our project demonstration video for RBE 522, Continuum Robotics.
A concentric tube robot is made of multiple thin, pre-curved nested tubes. By translating and rotating each tube relative to the others, we can steer the tip of the robot through the space. These robots are lightweight, can reach into narrow and curved spaces, and their motion can be predicted using beam theory and kinematic models. We first assembled the actuation unit and manufactured a set of pre-curved nylon tubes via heat setting them in 3D printed molds. Next, we configured the electronics and verified motion with a simple system test.
Our code takes a target position in XYZ or Cartesian space and produces joint variables consisting of the linear displacement and rotation angle of each tube to reach the target position. It does this by first checking its current location with Ford kinematics, taking the current joint variables and converting them into arc parameters. Then the Jacobian to convert these arc parameters to XYZ Cartesian space is generated using the physical properties of the tubes, and then used to generate the final end tip position. This Ford kinematics gets us our starting position, from which we can calculate our error. This error calculation process is then passed into one of MATLAB's pre-built-in optimization functions, where MATLAB recursively tries to determine inputs to minimize the error, resulting in an output of joint variables with approximately zero error, giving us the joint variables to reach our target end position.
To test our in-plane blending model, we performed a graph paper experiment. We recorded the end effector position for two configurations, a home position and an extended position where the tubes are translated to increase bending. We compared the measured tip position with the positions predicted by our forward kinematics. At position 1, our errors were about minus 8 mm in x and plus 6 mm in z-axis. At position 2, the error increased to about minus 14 mm in x and plus 14 mm in z-axis. The trend of our error was similar to the example provided in the course materials. We saw negative x error and positive z error. In our second experiment, we looked at out-of-plane rotation. We used our MATLAB function to predict how the bending plane rotates when we rotate the tubes about their axis. Then, we compared the predicted angles to the measurements. In the first case, the outer tube was rotated 60 degrees and the inner tube was 0 degrees. Measured angle was 45.51 degrees and predicted angle was 37.14 degrees. In the second case, both outer and inner tubes were rotated 60 degrees. The measured angle was 57.84 degrees and predicted angle was 60 degrees. In the third case, the outer tube was rotated at 60 degrees and the inner tube was at minus 30 degrees. The measured angle was 36.35 degrees and predicted angle was 27.24 degrees.
For the challenge, we implemented inverse kinematics for the robot using the Newton-Raphson method. At each iteration, we computed the task space Jacobian numerically, following the method described in the assigned paper, and we also tested a central difference approximation. Using this Jacobian, we updated the tube rotations and translations so that the predicted tip pose moved closer to the desired pose. We tested our algorithm on 5 distinct tip positions in task space. In all cases, the iterative solver caused the robot's simulated tip to converge towards each target, and we demonstrated corresponding motions on the physical robot approaching those same goal positions.